are now recording. We'll go from current slide. And that's what we got. Okay. Let me do a couple of announcements. I may have told you these before, but just in case. Number one, normally on Mondays and Wednesdays, like today, I would have office hours as soon as this class is over, 3:45 or so, until 5:15. However, today I've got a meeting on the Birmingham campus, so as soon as we get out of class, I have to book it to get to Birmingham to attend that meeting. It'll go until around 5, I think, and I've got to leave campus by 5:15, so I won't be coming back to this campus. I can't even get here by 5:15. Probably not. So I'll just stay on Birmingham campus the rest of the afternoon. Okay. So that's today. Now, before this week, on Tuesday and Thursday, the only office hours I had were 12:15 to 1:15, which is also my lunch hour. So it wasn't much of office hours, but I was in the office then because I usually eat in my office. However, starting this week, second mini-term, my second term physical science class doesn't start until 3:15. So now I do have office hours from 1:15 to 3:15. So Monday, Wednesday, 3:15 to 5:15, Tuesday, Thursday, Monday, 1:15 to 3:15, and Friday, 7:45 to 11:45. Okay. The bad news on that Tuesday, Thursday stuff is now I'm here on campus until 8 o'clock. So before it had been 6 o'clock. So that's where the 2 hours went. I'm teaching 2 hours later on Tuesday and Thursday. Now, I'm behind in getting grades on Gradebook in Blackboard. I had caught up on grading until today, and this many papers have come in today. So I've got those papers to grade, and then hopefully, knock on wood, I'll be able to upload them onto Blackboard, maybe tonight, but hopefully tomorrow, sometime in the afternoon. Okay? But I also have to get spring schedule finished, which is a monstrous change. So it will take me a while to do that. So I can't swear I'll get Gradebook caught up, but hopefully I can get it caught up by, if not tomorrow, Friday. If not Friday, sometime over the weekend. Okay. Those are the only announcements I know about. Any questions before we get started on today? Okay.
I'll be here next week, and I'll be out of town for my little brother graduate basic training.
Oh, wow. Yeah. And when is that? All week?
Just Wednesday.
Just Wednesday. Okay. You'll be here Monday, though.
Yes.
Okay. All right. We'll miss you. Okay. So let's do example 3, if there are no more questions. This is Chapter 2, First Order Differential Equations, 2.5 Solutions by Substitutions, Example 3, an initial value problem. Here's the problem. By the way, also, I don't know if you recall, I got a loaner computer from the IT department. It's similar to my other one. The difference is it's a smaller screen, but then within the screen, I can't write on the whole screen. I can only write on a little window of the screen. So that means I have a very small space to write, which makes it look like I'm writing bigger, but I'm actually writing smaller, but that's why it's sort of messy writing, because I'm having to cram everything into a little screen, so I have to do a lot of erasing. So sorry about that. Okay? Okay, let's get going. Example 3, bottom of page 74. Solve this. dy dt is equal to minus 2x plus y squared minus 7. Given that y at 0 is equal to 0. All right. Now, let's just take this from scratch. This is dy dt. No, dy dx. Okay, yeah. Okay, I can't read. Okay. I was going to say something looks terribly wrong here, and it is. I couldn't read that. It's dy dx. I said, you got x's, t's, and y's. How does that? All right, number one, you can't separate these variables. Okay? Sorry about that. No separation of variables. Number two, it's not a linear system because y is squared here. Can't have that in a linear system. Okay? Oh, what's next? Would possibly that be an exact system? I don't think so. Okay? And let's see, what else? Is it a homogeneous system? No, I don't think so. Well, yeah. Perhaps it is. No, it isn't because of that. This is a term. All these terms have x or y to the total of second power. S is to the zero power. Not homogeneous either. Okay, so what are we left with? Bernoulli? Is it a Bernoulli? Perhaps it can be. Okay? I think we're going to have to do a little bit of work to it to see if it is a Bernoulli form. Okay? So what I would suggest we do first is write it this way. dy dx is equal to, multiply this through, in other words, square that, let's see. Yeah. Okay, you could do that. What they suggest, and I think probably is a good suggestion, let's go back and do this. Since the name of this section is substitution, and it seems like a pretty logical thing to substitute here, let's let u equal negative 2x plus y. How about that? What's usually the next thing after you do a substitution? Then du is equal to, now, all right. What we want is u as a function of x, okay? So this will be minus 2, okay. Let's just go on and write it, du dx. That'll be easier, okay? That would be minus 2 plus dy dx. You see that? If u is equal to minus 2x plus y, what's in your square there? Okay. Then we have du dx would be minus 2 for that term, and dy dx for that term, right? So you take the derivative with respect to x. Derivative of minus 2x with respect to x is minus 2. Derivative of y with respect to x is dy dx. Okay? Now, what this says is that dy dx is equal to du dx plus 2, right? Okay. Which one? This one? This one? This is du dx, yeah. What I did, I added 2 to both sides. So dy dx is du dx plus 2. Okay? Now, let's go back to our original equation there. And what do we have? The y dx is du dx plus 2 is equal to, well, that in parentheses is u squared. Okay? Now, let's take a look at that and see if that is a Bernoulli form. Okay? I think we can almost get it there. Here's what I would do. I would subtract 2 from both sides and add u squared to both sides. Okay? That becomes du dx plus u squared is equal to minus 2. Okay? Now, is that in Bernoulli form? No, not quite. Okay, let's back off a moment here. Oh, I messed up. Sorry. I knew I was missing something, but I wasn't seeing it. I forgot to write my whole equation. Okay. It's dy dx, which is du dx plus 2, is equal to u squared minus 7. I forgot that part. Sorry about that. Okay. Now what they suggest is subtract 2 from both sides. So now that becomes du dx is equal to u squared minus 9. Okay. Now that's a little better. Now that one, we can solve that by separation of variables. Okay? Right? Let's do it. This is du over u squared minus 9 is equal to dx. Right? Divide both sides by this, multiply both sides by that. There you have it. Okay. Now, I need more room. Okay? So I think I can erase, I sure hope so, this. I want to keep my original problem, and I want to keep my substitution. And I think all this is correct, so I'm going to delete this. See, this small screen, I just can't write very much on it. I wanted to keep that, I think. No, just this bottom part. Okay? So I'm going to write this up at the top now. du over u squared minus 9 is equal to dx. Now, so I'll erase it at the bottom. Now, one thing I haven't done, and I guess it's a good time to do it. Okay? When x is equal to 0, y is equal to 0, right? That's what we were told there. So when x equals 0 and y is equal to 0, u is also 0. So I think we may come back and plug back into y, but I think you can say u of 0 is also 0. Okay? I think we can do that. We'll see. We'll come back to that in a minute. Okay? Now, let's integrate both sides of this. All right? I can integrate the right side. That's just x, okay? On the left side, however, this looks like a partial fraction. So let's take this over here and do that. The integral of du over u plus 3 times u minus 3. Okay? You might try a secant substitution, but I think this might be easier. Okay? Let's see if it is. Okay? So we have this 1 over u plus 3 times u minus 3. Partial fractions, that would be a over u plus 3 plus b over u minus 3, right? Remember partial fractions? Okay, let's multiply both sides of the equation by u plus 3. No, by the whole denominator. U plus 3 times u minus 3. Okay? Multiply this by u plus 3 times u minus 3. Multiply this by u plus 3 times u minus 3. Okay? Over here, everything goes out except 1 is equal to, here the u plus 3's go out, and you have a u minus 3a plus u minus 3's go out here, and you have bu minus or plus 3b. All right? See what we've done? What's that? Yeah. The denominators go away, which is what we wanted. A lot easier to work with numerators. All right. I probably shouldn't have multiplied through yet. But the first thing we're going to do, let's let, it doesn't seem fair, but it works, let u equal 3. Okay? And when you let u equal 3, then this first term here goes to 0. So you're left with 1 is equal to 3b plus 3b, okay, which is 6b. So this tells us that b is equal to 1/6. Okay? Now let's go back and let u equal minus 3. And when u is equal to minus 3, you get 1 is equal to minus 6a, and then you get minus 3b plus 3b, that goes to 0. So this implies that a is equal to minus 1/6, if I could write. Okay? So now this integral here becomes minus 1/6 the integral of dx over, du over u plus 3 plus 1/6 times the integral of du over u minus 3. You just plugged in what a and b were here. Okay? Well, this integral right here is log, natural log, of u plus 3. And this one, with a minus 1/6 in front, I don't know where my minus sign went, there it is, plus 1/6, the natural log of u minus 3. Okay. And then you can add a plus c if you want to. All right. Well, yuck. I'm out of room again. So let's erase again. And this time we'll erase this and this. And all this is equal to x. Can't get that to erase. Okay, you don't see the eraser going. It's going like crazy and nothing's disappearing, but very slowly. I've never seen it this slow. And it just happened overnight. Yesterday was great. Today is so slow, it's pathetic. And I don't know why. Okay. Whew. All right. So what we have here, I'm going to rearrange the order a little bit and adjust it a little bit. This will be log of absolute value u minus 3 to the 1/6 power minus log absolute value u plus 3 to the 1/6 power. And that's equal to x. And you may have a plus c there. We'll fiddle on that a little bit later. Well, let's write this like this. The log of absolute value u minus 3 over u plus 3. We'll just do all absolute value there, raised to the 1/6 power. Okay? And that's equal to x. I want to say x plus c. Yeah, let's go and put x plus c. Okay? Let's take an e of both sides. E of that is just going to be that. U, absolute value, u minus 3 over u plus 3 to the 1/6 power is equal to e to the x times e to the c. So I'm just going to call that c e to the x. That's a different c from before, but it's okay. Okay? Now, let's raise both sides to the 6th power. Okay? So let's make that yet a different one. Have u minus 3 over u plus 3. Raising it to an even power is going to make everything positive, so I think that's going to be okay. And I'm going to change the c again, c to the 6. That's going to be our new c, e to the 6x. Okay? Now, let's go back and plug in what u is. U is minus 2x plus y. So this will be y minus 2x minus 3 over y minus 2x plus 3 is equal to c e to the 6x. Okay. Let's see if that's what they get. Okay. We're going to need a little bit of manipulation here. So I'm going to have to do some erasing to see if we can get it into that form. And I sure hope I haven't made any errors, because I sure don't. I'm not going to go back and try to find them, because I've erased too much. Let's erase lots of this. I want to keep this part up here. Okay, and I think I want to erase everything else. But it won't erase. It's erasing so dreadfully slowly that I can't even tell. I erase it many times. Sometimes it goes off and sometimes it doesn't. I've never seen it this slow. Ever. 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 It's one line I can't get to erase. That whole set of numbers I can't get to erase. This is so unbelievable. It's so slow. There. Okay. Here's my manipulation. Here's what we got. Y minus 2x minus 3 is equal to c e to the 6x times y minus 2x plus 3. What I did, I multiplied both sides of the equation by this denominator and get rid of the denominator. Okay? All right. I'm wanting to solve for y. Okay? First thing I'm going to do is add 2x plus 3 to both sides. Okay? Next thing I'm going to do is multiply this through. So that'll be y is equal to 2x plus 3 plus y c to the e to the 6x minus let me get it in the form they have it. I don't know. 2c e to the 2cx e to the 6x plus 3c e to the 6x. Okay? So I'm going to subtract this term from both sides. Okay. And I may have done some more things wrong, but I have no more room, so I've got to go back and erase some more. Sure, I hope I haven't made a dumb mistake, because it's going to be impossible to track it down. Okay? So what we have is y times 1 minus c e to the 6x is equal to 2x plus 3 minus 2cx e to the 6x plus 3c e to the 6x. Okay? Okay. All right. Now, these two terms have x's in them. In fact, two x's in them. So that's going to be 2x times 1 minus c e to the 6x. These two terms have plus 3's in them. That's plus 3 times 1 plus 3. No, 1 plus c e to the 6x. Okay? This is so aggravating. Okay. Okay, is that a plus or a minus? Oh, wait, no. They're treating it as if this is a plus here. Let me see if they're right. They did it slightly differently. But here's what they wound up with. Y is equal to 2x, which I think we've got okay, plus 3 times 1 plus c e to the 6x divided by 1 minus c e to the 6x. Now, I've got something a little squirrely on mine, but that's what they get. We were coming awfully close to it. Okay? Now, got to erase some more. Sorry about that. Let me erase this. Okay. Now I may have made just having to erase so much and then forgetting what I had. This is such a pain in the neck. That was one advantage of writing on the boards. I could just fill the whole boards with one problem. I have a very small board now. I can't get that mark to erase. There we go. Okay, I'm going to rewrite this one. Y is equal to 2x plus 3 times 1 plus c e to the 6x divided by 1 minus c e to the 6x. Okay, that's what they got. No. I know where the error came in. Sorry about this. I need to go back and erase these again. I still may have a little error here, but I think it's going to clean up in just a second. I hope so anyway. What I forgot is to plug in my y0 equals 0. Okay, let's say that we've got it right there. I don't know that we do, but let's say we do. Okay? So let's take this and divide both sides by 1 minus c e to the 6x. Okay. Now let's put y, when x equals 0, y is equal to 0. So that's going to be 0 there. No, okay. This will be, yeah. 0 is equal to, if we divide this by 1 minus c e to the 6x. Okay. So those go out. 0 is equal to, this will be 0. So that's whole term 0. 3 plus c times 1 over one minus c. Okay. So, yuck. No, I think I missed that here. 3 plus, that's going to be 3c. Yeah, 3 plus 3c over 1 minus c. Well, multiply out the 1 minus c. So this basically gives us that 3c is equal to minus 3, c is equal to minus 1. Okay, that's what the book got. So I think we're okay there. So now let's go back and plug in c is equal to minus 1. Okay, so let me erase again what? Oh man, I just don't have room enough for anything. Let's erase all this. Now I may have gotten something off somewhere there, but it's looking okay now, I think. If I'm not mistaken, this is my y. So let's plug in a minus 1 for c. So y is equal to 2x times 1 minus e to the 6x plus 3 times 1 minus e to the 6x divided by 1 plus e to the 6x. Okay. Now with that in there, we're going to erase this stuff at the bottom now. I hate to do it this way. Now I may have lost a sign somewhere here or something, but here's what the answer they get. This is where I'm going to write it down now. Okay. Y is equal to, they have the 2x in front. I don't know if mine reduces to that. Plus, and up here, I think I changed my sign and I wasn't supposed to. So I think it does work out this, but I changed because I got they convinced me to. 3 times 1 plus c to the e to the 6x over 1 minus c e to the 6x. I think I messed up by letting them talk me into something when I shouldn't have done it yet before I did the c. But anyway, that's what they get. Oh, wait. There's no c in there. We already plugged in for c, so I shouldn't have this one there. I'm sorry. It's not erasing anything right now. I don't know what's wrong with it. Whoa. There, now it's erasing. I should have taken out these with the C in. Okay. Okay. So y is equal to 2x plus 3 times 1 minus e to the 6x over 1 plus e to the 6x. Okay. That's what they got when you plug in the thing. Sorry that took so long. They do show a picture of the graph. And with the C's in there, you have a whole family of curves, but you want the one that when x equals 0, y is equal 0, so you want the one that goes to the origin. None of the rest of them do. That blue one does, so that gives it to you. Now, when x's get quite large, this goes to 0, and you have this 2 plus 3 over this thing. When x's get quite small, then this one goes to 0, goes to 1, and you have just the top part. So this is the large x's, this is the small x's. In between them, there's some variation. Okay, that finishes 2.5. Homework exercises. Any of the odds 1 through 13. Okay? I'm sorry, 1 through 9. Any of the odds 1 through 9. Either 11 or 13, or both. Any of the odds 15 through 21. No. 15 to 19. Do 21. Do any of the odds 23 to 27, and do 29. The discussion problems here, I don't know if you have a book. The discussion problems here, you don't have to do them, but they mention Riccati's equation. Okay, it's a differential equation. So if you haven't picked a paper topic yet, you could say, who in the world was Riccati? You know, how did he come up with the differential equation? What was the purpose of the differential equation? What problem did it solve for? Okay? Already we've had the Bernoullis. Any of the Bernoullis you can write on. And then, so that's another one there. And there's one more thing listed here. Population growth, it says, follows this logistic equation. Okay? I'll just tell you. Not only population growth, or not only population of people, population of animals, populations of deer, populations of bacteria, populations of viruses, in other words, diseases follow this logistic equation. Epidemics follow this logistic equation. So that's an equation that you have lots of applications of, depending on what area you're going into. What are you, mechanical engineer?
Civil right now.
Civil? Okay. Don't know if you'll be dealing with population growth thing, but there are all sorts of problems that do. Okay. Now, let's do a little bit on numerical methods. That finished 2.5. 2.6, numerical methods. All these techniques, all these tricks, all these procedures that we've done so far may solve 1 every 10 or 12 differential equations you ever run across. Most of the differential equations you run across, you're going to have to solve numerically. So that's why this section is somewhat important. Differential equation can be a source of information. We started the chapter by observing that we could garner qualitative information. We examined first-order differential equations analytically, developing some ways of getting either explicit or implicit solutions. But a differential equation can possess a solution and yet not be possible to obtain in differential equations. Let's see, skipping a line. Yeah, analytically, not be able to solve it analytically. So what we do is try to solve it numerically. In this section, we're going to develop the simplest of the numerical methods, a method that utilizes ideas of a tangent line can be used to approximate the values of a function in a small neighborhood near the tangency, point of tangency. Okay? So here's the assumption. Let's assume that a first-order initial value problem, here's the problem. Let me erase all this on the slide. Okay? I've got to sneeze. Sorry. Trying not to. Y prime is equal to f of xy. Okay? Given that y at sorry. I fought it as long as I could. Sorry about that. My head had been clogged up ever since lunch. I guess it's this cold air blowing on me. I don't know. But now that's the first sneeze, and boy, that's I don't know what it's going to do to me. Y at some value for x, we'll call it x0, is equal to some value for y. We'll call it y0. It could be y of 7 is equal to 15. Y of 0 is equal to 0. Y, anything. Okay. If we assume that there is a solution to this, one way of approximating the solution is to use the tangent lines. So, for example, let y of x denote the unknown solution of the first order initial value problem, and here's one. Y prime is equal to 0.1 times the square root of y plus 0.4 x squared. Given that y of 2 is equal to 4. Okay? Now, that's not separable. It's not linear. Square root of y is not linear. It's not exact. It's not homogeneous. It's not Bernoulli, okay? None of the things we've done analytically can come close to solving that. Okay? So what we're going to do then is come up with approximate numerical values of that unknown function, y of x. Specifically, suppose we wish to know the value at y is equal to y at 2.5. So here's what we're interested in, y at 2.5. That's what we're looking for. Okay? We know that y is at 2 is going to be 4. Okay? Now, 2 is not too far from 2.5, so we're sort of guessing maybe it's not going to be a lot different from 4, but it probably will be different from 4, okay? So what we can do is plug in and see what the slope of y is at 2. We know where it is, and 2 is equal to 4. Let's find the slope. And then we'll go over a little bit, maybe 2.1, do a little bit of the change of x, and find out what the slope is there. And then another one, and another one. So we'll inch our way along until we get close to y of 2.5. That's the general idea, okay? So, okay. All right. So we'll do this slope. And they keep changing so many things here. So let's calculate y prime at the point 2, 4. Because we know when x equal to, y is equal to 4. So let's calculate the slope at the point 2, 4. We know the value, let's calculate the slope. Well, the slope at 2, 4 is going to be 0.1 times the square root of 4, that's the y value, plus 0.4 times 2 squared. So that slope is going to be 0.1 times 2 plus 0.4 times 4, which is 0.4 plus 1.6, so this will be 2. Okay? That's going to be the slope at that point. Okay? How did they get 1.8? No, point. I'm sorry, I can't add. I was thinking. I can't write is what I can't do. I changed this 1.1 to 0.2. Okay. Sorry about that. Okay. So no, I'm doing it. No, it's a 0.1. This will be a 0.2. 1.6 plus 1.2 is 1.8. So there's the slope at 2, 4. Okay? Now, okay? Slope at 2, 4. Now, what we have now is, let's assume that the function is going to travel from here in a linear fashion along that tangent line, because the slope is 1.8, so it would be 1.8 times x. Okay, we're going to make a linear assumption. Assume a linearization here. Okay. Now, where did they get the 0.4? Okay. see where they get the 1.8. Where do they get the plus 0.4? Man. Okay. Let's give it a shot and see. Let's just say linearization is 1.8 plus b. Okay? Now, the point slope form is y minus y1 is equal to m times x minus x1. Okay? All right, so let's say y minus 2, no, yeah, y minus 4 is equal to 1.8 times x minus 2. Let's just see what happens here. Y minus 4 is equal to 1.8 x 3.6. Yeah, that's where they get it. So add 4 to both sides, and you get y is equal to 1.8x plus 0.4. Okay, that's where they got it. So, no. Okay, that's our approximation, okay? Now, we're going to say it's going to follow that line for a little ways. That's your tangent line, okay? We just did it by the point slope formula. So let's say that little ways will be up until 2.1. So then our next guess, y1, is going to be L of x1, which is going to be 1.8 times 2.1. We're going just a little bit further, plus 0.4. Okay? Let's see what that gives us. If you got a calculator, do you? 1.8 times 2.1 plus 0.4. That's not what they get. No, it can't be. Okay. 1.8 times 2.1 plus 0.4. Ah, good. That's what they got. 4.18. Okay, that's what they got in the book. Okay. So that's your next point. Okay? When x equal 2.1, y is equal to 4.18. Okay? So guess what we do next? We go back in and plug that y and that x into our formula and get a new slope. Then we do a new linear approximation. Then we plug in a 2.2 and see what happens there. see what we get as a y, and then plug that in. And we keep crawling up like that, however it's going, until we get to 2.5 and see what it comes out to. That's called Euler's method. By the way, there would be a potential paper topic. Who in the world was Euler? Okay? How did he come up with this method? Why did he come up with this method? Okay? What would he get? Okay? Now, the good news is you can do this on a computer far faster than you can even with a calculator. Okay? All you do is put in your function there. Okay? And every time you need it, you just call up the function that calculates it. That gives you a new y for a given x, and then you do another linearization function that gives you a new y value for that given x. Okay? And you creep along like that until you get to 2.5 and you stop. Okay. Now, your generic form then, this is when you do all this stuff to it. I'm going to erase all this and jump to the conclusion here. Okay. Y of n plus 1 is equal to y of n plus h times, h times f of xn, yn. Okay. Now, this is combining what we just did into one formula. Okay? We start with the x sub n, whatever our initial value is. Initial value is. When x has a certain value, y has a certain value. Okay? So that's going to start off being our 0. We're going to calculate that function. Our original form said where was it? Yeah. Y prime is equal to some f of xy. That was our original thing with an initial condition. Y of 0 is equal to y of 0 is equal to f of y at x 0. I couldn't get that right. Okay. Y at x 0 is equal to y 0. Okay, there's your initial condition. Okay? So, we start with this value, x0, y0. We plug in this x0 here, y0 there, operate out with the function. That gives us a slope there. Okay? Now, so that's this function value here. That is your slope to begin with. Okay? You add to y0 some increment. Okay? Some increment, h. If you decide that ahead of time. Last time we were doing 0.1. We started at 2. We're going up to 2.5 and did 0.1. So our h was 0.1. So 0.1 times this add it to that. That gives us a new y1. Okay? Xn was x0 plus h is going to be the next x1. So you add the h to xn. This gives you y, that gives you xn plus 1. This gives you yn plus 1. And then you do it again. Okay? And then your yn plus 1 plus h, whatever the increment was, times alpha n plus 1, y of n plus 1. You recalculate this every time, and you creep up whatever it tells you. You're going along there, and you try to get to a solution. So it's a combination of what we were doing. That's called Euler's method. Okay. So it's just successive tangent lines. Okay, we're out of time. We're going to have to pick up that example 1 next time. So remember the formula. Okay, well, we'll go back over it. All right, glad you were here. Did I mark you here? There you are. 238. Victor was here, but the other two were not. Okay, got it. Then we'll see you on Monday.